I am here to talk to you guys about quantum random number generators. So my name is Pooser. I've got two guys in the lab helping me out. They're not here. Oh, actually, I forgot one of their names. Is there a laser point? Yeah. Brian Williams is another guy. He'll be in the lab today to talk to whoever wants to come. And Ben Laurie as well will also be in the lab to talk to whoever wants to come see this. So quantum random number generators, they're kind of interesting because randomness is interesting. Randomness is, everybody knows, is super important. So randomness is important because we need them for HPC. Actually, we need them for simulations. Right now, most simulators use pseudorandom number generators. National security, of course, health data security. There has been a few actually now database hacks based on weaknesses in password generators or password hashing algorithms now for health science firms. Grid security, so by grid I mean electric grid actually, so logging in and out using multi-factor authentication for devices on the grid. And I've done a little bit of work in that area and can tell you that there are some currently in certain places on the grid some big security holes there based on authentication. And we have lots of programs here at ORNL just focused on fixing those issues. So random numbers are important for that because they're important for multi-factor authentication. Another area where they're very important is, well, you know, we all have multi-factor authentication products now on us. I've got one in my pocket here. This one's been hacked already a couple of times too, by the way. So that's my next bullet. 2011 RSA hack. Of course, you probably have one on your phone now too. Google has an authenticator app. None of those things use QRNGs yet. So most of them use pseudo-random number generators. I'm trying to point, we can't point at that one. So most of them use pseudo-random number generators, and one of the issues with them is intrinsic periodicity. All pseudo-random number generators actually are periodic, in fact. And in principle, okay, you can make the period millions of digits long or trillions of digits long. That's fine. But in principle, all of them have periodicity. In principle, all pseudo-random number generators are reversible, including one-way hash functions that generate random numbers from a seed and actually random, right? We all know that one after the other hash functions get reverse engineered via collision attacks and things like this. So, yeah, these work for a lot of things. These work for a lot of things, but they have shortcomings if you're very paranoid about security. Oh yeah, here's one where my information was hacked. There was like several tens of millions of people. Their information went out. This one could have been prevented with better random numbers, by the way. So yeah, my information's been hacked and leaked on the internet multiple times because of bad random number generators. There's one most recent one. I think 140 something million people. I went ahead and froze all my credit. They've found out there's a fourth one, by the way. There's this used to be only 3. Now there's a fourth one called Innovis. Like, does any random company just get to come up and say, I'm going to deal in people's personal information with terrible security anytime they want? I don't know. So in the future, you may need to freeze 5. But if they were using good security based on true randomness, we may not be here. Anyway, you guys may have heard this guy named Bruce Schneier, very well-known security expert. He's got a blog called Schneier on Security. He's a consultant for multiple DoD agencies and so forth about how to make their security better. He's been quoted, and many people have been quoted as saying the weakest thing in some of our cryptography chains right now is the random number generator, actually. In a NIST specification that actually was not even released yet, was just getting ready to be released, the very next, so SHA 256, then SHA 512. NSA had provided NIST with a random number generator. Said, hey, this is good. It's really fast. And it's still really random. And some independent people what NIST does before they put out specs is they ask people to independently test these specs before they go. Well, a whole bunch of people discovered backdoors, specifically in the random number generator that was provided for this next SHA specification. That's pretty interesting. I think it was, so this is the one I'm talking about, the dual ECD RBG. Yeah, and it was pretty bad, rendering SSL as clear text. So that may sound familiar. That's what the heartbleed bug, I think it was called, about maybe a year ago, was doing to everybody on the internet. So we need good random number generators so we don't render SSL as clear text, among other things. So the solution against all of this is so-called true random number generators. So true random number generators, actually this is more specific. I want to say quantum superposition of photons on a beam splitter, but actually you can make a true random number generator out of any physical process that can be described by quantum mechanics. Okay, actually it's just that most of the ones out there right now in public that you can actually buy some of these are based on this concept. Put light on a half mirror, and some of the light goes that way, some of the light goes that way. It's like a 50-50 coin toss. So that's how that works. It's based on the concept of quantum superposition. You can buy them right now for a few $1,000s. Usually they don't go below $1,500. They're okay in terms of bandwidth, a little bit slow, but it depends on what your application is. So to get 4 megabits a second of true random numbers coming out of one of these devices, you're looking at this kind of, you're looking at 2,000 kind of price. This number way up here for these actually to be released by some of the potential competitors on what they call online encryptors, or sorry, online entropy sources for their encryptors. So you put a rack mount device in that's just spewing out random numbers, broadcasting it to your internal network, and anybody who needs a source of entropy can grab those numbers. They've actually got things in the work, but those are expensive. The problem with these so-called true random number generators is that they're based on quantum theory. They're based on theory of quantum mechanics. And, well, in the lab, things don't always turn out when we do things in the lab the way they were intended in theory. So, yeah. So there are a few things that can go wrong when we try to make a true random number generator based on quantum physics. And one of them is that we may still end up with the same problem, actually, that the pseudo-random number generators have. We may still end up with bias that's brought on by periodicity. And actually, this is not really that big a deal. I put this as a potential shortcoming. It'd be nice, there are random number generators out there published in the literature that don't require extractors. So an extractor is a one-way function I was telling you about before. It's just a way of increasing the entropy of a distribution of numbers. So I've got a bunch of numbers, and let's say it's 1 bit per bit of entropy is the max entropy I can get. Let's say I have like 0.9. Well, I can put it through a one-way function, like a hash function, or a Toeplitz extractor, and get it up to very close to 1, like 0.99. So it's not really a big shortcoming, but we use these to mask this shortcoming. And this shortcoming is a big one still, because as I told you before, these one-way functions are in principle reversible. And so if you can reverse this part, then you get back to here, and now you have bias. If you have bias, the reason why bias is bad in a distribution of numbers is because it gives a hacker, or it gives Eve, we call her Eve, it gives Eve a best guess as to what your random number could have been, a peaked distribution. If she's going to always try a strategy of just guessing what the number would be, she's going to try to guess at the peak or the average of the distribution. And depending on how peaked or how biased it is, she'll be right that often. So that's the idea. That's why bias is bad. It's also bad because you can use it to reverse engineer other things that use those numbers as seeds. So our idea is, of course, to try to get rid of these shortcomings. That's why I put this slide. The whole point of our product is that we are dealing with each of these things. So we actually have a whole bunch of quantum random number technologies at Oak Ridge and applications that are patented. So this is one of them. So this one is interesting because it uses the arrival time of photons at a detector as a random variable. So that's interesting because if you look over here, this is what's called a tapered diode. Turns out that electron hole pairs, you can force them to combine at a diode, right? That's when you forward bias a diode in electronics, current flows. current flows in a photodiode, it emits light. But for every electron and hole pair, those are quantum particles. When they recombine and emit a photon, it's a random process in terms of when it happens. It's like if you've ever studied atomic physics or quantum physics at all, when atoms get excited, like a hydrogen atom, when its electron gets excited, sometime later, the electron's going to de-excite and go to the ground state. That's called spontaneous emission. That's a quantum mechanical process that we can actually measure the time associated with that spontaneous emission. That's what this is. So some current comes in, sometimes some electrons and holes recombine in a spontaneous and random way, and we just need to ask ourselves, when did it happen? We don't know. We can't determine with absolute precision when it happened. That's the whole point. That when it happened number that we're trying to measure, that's the random variable. We can only determine it with a certain amount of precision, and the noise around it is a source of entropy for us. It just happens to be that that noise is described by quantum physics and not by any classical theory, which means that we can rest assured that the noise, the numbers are derived from an irreversible source. So here's how it works. You got this laser or this amplifier diode thing. It's literally this simple. Diode followed by an optical detector. And we just use an FPGA to clock the arrival time of the photons on the detector by checking when the clicks occur on the detector. So this guy just outputs a pulse when the detector sees a photon. And we have an FPGA over here that just says, okay, it's an edge detector, essentially. And so it's got its own clock, and that will set the bit rate of our QRNG, actually. So let's say we run this FPGA at 400 megahertz or so. It can detect an edge once every, 1 over 400 megahertz, whatever that is. And so we then just say, in this time bin, was there or was there not a click? And so that's our coin toss. Okay, so the bit 0 equals there was a click, the bit 1 equals there's not. And we end up with this kind of distribution. So the probability of a click is an exponential decay as a function of time, which is normal. This is a Poisson or super Poisson distribution. That's good. That Poisson distribution is a hallmark of quantum randomness. So what we do is we just bin this in order to ensure fair sampling. So if you got a click this far out in time from when you started waiting, you should make that bin bigger so that the area under the curve is constant for all bins. That equals a flat distribution, which I think I have somewhere. I'll have to show it later. I should have put it on this slide. Basically, you bin this right, this exponential becomes flat. I'll show it in a minute. We have a bunch of other QRNGs in the lab. So this one's actually been shrunk down considerably. This is an old bulky one. But you can see that the actual device is, at this point, it's close to microscopic. So very easy to integrate. We have here a heat sink on it that's actually unnecessary, it turns out. You can operate these things at very high powers to get very high bit rates. But if what you're interested in is very high quality random numbers, but not huge bit rates, and by huge I mean gigabits. If you're interested in, say, hundreds of megabits, you can actually operate this thing completely uncooled. Right now, we cool it to 18 Celsius, but you don't have to. You can just operate it at room temperature without all that stuff so that you can then integrate this onto a chip. This is just a piece of silicon, so it's pretty compatible with it does take a little bit of current, so these little wires here send all the current to it. But again, when you're operating it in this mode where we're operating it, which is not where a device like this is typically operated, it's spontaneous emission. You only need milliamps to operate the device. So we'd send like a couple of milliamps to it, and we'd get, we're talking attawatts of photons out, picowatts, attawatts of, femtowatts, sorry, to attawatts of photons out, and we can detect those with our single photon detector. So the downside of this design is that this detector is an expensive piece, and this has been a downside to all quantum random number generators to date. These detectors are expensive because you can imagine that a single photon being a quantum object is hard to see. We have a way around that I'll show you in a minute. But I just wanted to let you know, this is a patented QRNG that we have here. We don't have a demo of this one in the lab right now. This one we've shown is, it passes the randomness tests. It's, getting bit rates of 100 megabits a second or so. But it can be scaled up by increasing current. And then here's some stuff on an optics table. So we make all of our random number generators with light, and then we integrate them later. So this one here is one of these tapered amplifier-based ones. It's about this big, so it's not small, but it's also the same size as all the QRNGs you can buy right now. The point of what I'm talking about here today is that we're making them a lot smaller, which I'll get to in a minute. But I just wanted to show you some of the other ones we have patented. This one is very simple. It's just light beam splitter that we actually use a digital micro mirror device as the beam splitter. Basically, if that's a DLP projector, it's what's inside there. So those are already fairly well integrable. We split the light and send it 1 to 2 detectors. It's very simple. Light source, splitter, detector. That's it. That's all you need for a QRNG. And it really does work. So we've been working on integrating this onto a circuit board. And so I'll show that in a minute. We have some applications for QRNGs that are patented that I thought you might be interested in. So again, I talked a little bit about authentication at the beginning. So this is an application where we use a QRNG as a source for authentication. So, so this box here represents the QRNG. The numbers that come out now, they're digital numbers now. So let's say they're 8-bit numbers, okay? So you have a token and you have a server. So the token, which actually can be a piece of software at this point, right? It doesn't have to be the physical device I got in my pocket now. The token has random numbers on it that it gets one of 2 ways, and I'll show the second way in a minute. The first way is pre-shared key distribution, and that's how all hardware tokens currently work. So that's how this works. This does not actually generate random numbers on the fly like it looks like it does. When I stare at it and the number changes in 30 seconds, it's not a new random number. It's actually a seed, a single seed that's provided to it at the point of manufacture, and then there's a hash chain. That number is hashed over and over and over again to make it look like a new random number. The entropy is actually exponentially decaying as a function of time. The more you use random numbers and reuse them, the less random they're going to look to you and others who might be observing, okay? So we can do that, though. That's not a problem. We can share our quantum random numbers via a pre-shared key. The way to get around that problem that I just described to you about an exponential decay of entropy as a function of time is simply provide a list of random seeds rather than just a single one, store them in a protected memory so that nobody can hack the server and get them, and you can hash those pre-shared keys if you want to, and we do that. So, okay, here's how it works. Pre-shared key goes to the server, goes to the token. They're distributed. I buy the token. Somebody else buys the server. We don't do any more random number distribution now. Now we're going to synchronize. We're just going to ask, when did the user ask for an input, just like the RSA token currently works. And all multi-factor authentication stuff that way that's not based on text messages works that way now. So, okay, so we have a random number. We enter some random numbers into a computer, and we just ask the server, was that the random number you had? Innovation that we provided was that you shouldn't just store this guy in memory on the server, which is what hurt RSA actually. They took away several gigs of seeds in 1 second. Just by getting on the server and downloading the clear text. So that's probably not a good idea. So what we do instead is we provide a separate device, and it can even be accessible over USB. And so we've implemented this via what's called a gum stick. It's an ARM device that's about this big. It's got a little screen on it. To serve as our protected storage, and that talks to the server via USB. They just ask, what time is it? And the protected storage says, well, it's 10 o'clock. You're not due another random number until 10 o'clock plus 30 seconds, so I'm not giving you one. So you can't just log into the server and download all the seeds at once. So computer says, if I'm allowed to have a random number, does it match that one? If it does, then okay, he's allowed to log in. So so it's a two-factor authentication system based on quantum random number generation. But you don't have to, an interesting point here is you don't have to have a QRNG in your pocket. That's something that a lot of people, I'm not saying you guys think this, a lot of people think this when they come to me and talk to me, and they just don't understand. If your QRNG is random in your pocket, my QRNG is random in my pocket, how the heck are we supposed to synchronize? That doesn't make any sense to me, because that's not how it works. You have to distribute the keys, okay? Random keys are good, but you got to distribute them. So another way to, and this is just what I was telling you guys about before. You can make a hash chain, but just switch the seed. So if somebody happens to get a hold of this seed or reverse engineer this hash function, at least the seeds came from a true random source, so you just switch to the next seed. So, for instance, in this case, it could be stored on board on memory, a gig of seeds. This is dirt cheap these days now. It could last you 10 years. But you could also just do it now in software on your phone and store it in everybody on their phone now has protected secure credential storage on their phones. It's how I'm able to log into my work email. It's a whole separate space. We can store true random keys right there on the phone. So that one, we have an invention disclosure on it. I'll show in a second. One of the questions we get is, why is this random? Okay, you're talking all this hocus pocus about quantum physics, and why is it random? And I kind of described it a little bit at the beginning, but I want to go slightly deeper into that. So this is a picture, by the way, of one of the devices we got in the lab. I think we have an actual photo of it later. So, it's what I told you before. You have this source of light. It doesn't have to be a laser, but here I'm showing a laser. Source of light, it hits this beam splitter. It either goes this way or this way, and we ask, which way did it go? And that was my 50-50 coin toss. But why would that be any more random than a coin toss or rolling dice, right? It's because it accesses the concept of quantum superposition. So this thing is a wave function, actually. And when I go through this beam splitter and I hit these detectors, I'm doing a measurement on a quantum superposition. It turns out quantum superposition, the concept of it, a measurement on that in what's called the Copenhagen interpretation of quantum mechanics says that the output of that measurement is completely random. Actually, we have no control over what the result of a measurement on a quantum wave function is. Now, we can certainly induce a lot of bias. We can actually induce so much bias that we measure that wave function in what we call a basis, in which there's only one term in the superposition, which means that, yeah, you have a 100% chance to get the one result. That's bad. That's 100% bias. You can also engineer quantum wave functions, though, in such a way that they have, say, two terms in them. I have a chance for a photon to go this way or this way. The wave function looks like 50% chance to go this way plus 50% chance to go that way. That's what we call the superposition. When I do the measurement, the superposition so-called collapses. It ended up being either one way or the other. Some people have a problem with the concept of a wave function collapse. Einstein did. They said this is the wrong way to think about quantum mechanics. And it's wrong to think that it's random. It turns out it doesn't matter how you think about it. That actually is unimportant. You can be a realist and say it was always one way or the other. I just had limited knowledge of it. That's okay. If I had limited knowledge of it, but quantum mechanics predicts I can only obtain so much knowledge about it, then that's equivalent to randomness. Some people, the definition of randomness is absence of information. Others, it's entropy. Entropy is, mixing information with thermodynamics. But the point is, if I don't know which way it went, it doesn't matter whether a wave function collapsed or whether it's due to my inability to do a measurement on it, right? Quantum mechanics predicts either one, and you can choose whichever interpretation you want. The result is the same. And here's the other way of thinking about it that I just talked about, the Heisenberg uncertainty principle. So here I said it's a wave function that collapses to either this way or that way. Well, here I'm going to tell you, Heisenberg said, I just can't figure out, when I do a measurement, I just can't figure out the results exact. I can't measure with infinite precision two non-commuting variables. That's something that we can exploit to generate randomness, to generate entropy. So here's an example. This is the most math that we're going to have. And I'm going too slow here, too. So strap in. No. So this is how we would plot a measurement on a source of light in what's called its phase space. So the source of light has an amplitude and a phase. I call x and p. Heisenberg uncertainty principle says the noise on x and the noise on p product cannot be smaller than this very tiny number, h bar over 2. Well, we can access it. It's maybe small, but we can access it in the lab, and that's what we do. When you try to measure the amplitude of this light field, you end up with a result that's random to anywhere within this circle. You have no control over where it's going to be in that circle. It's just random. And so that's what we access to generate entropy. So the uncertainty ellipse is given by that function. So a measurement on X or P can't be absolutely precise. So that a lot of people have, in the early days of quantum mechanics, had a problem with that. Instead, what we do is we exploit that fact because what we want is randomness. So actually, we just measure noise to get our randomness. So a lot of people say, oh, well, I measure noise. I measure the Johnson noise on a resistor. I measure the noise of the atmosphere. I just turn my channel on my TV to some random channel, and it's white noise. There's a big difference. And the difference is that the noise associated with classical processes, even chaos, is 100% deterministic if you know the initial conditions. That's equivalent to reversing a hash function, right? You reverse the hash function to go back and get the seed. If I knew everything there is to know about the atmosphere, I could tell you exactly what the white noise on your TV screen will look like, in principle. Some people are so paranoid that that's a big problem. This here, it doesn't matter how much you know about this quantum state. You'll never be able to get the knowledge that's inside that circle. That's where the entropy comes from. Okay, so let me just skip through this real quick. Or not skip, but go quickly through this. This is the self-correcting concept that you saw in the pamphlet. So the idea is that you can introduce bias by not doing this measurement properly. In other words, this may not be 1 over root 2 here. This may not be 1/2 probability. So what we do is we do what's called a weak measurement, where we ask a little bit about for a little bit of information about the light, and we use that information to feed back onto the source of the light or onto the basis of detection, and we just nudge the basis in one direction or the other to remove the bias. So this concept here is one of the patents that we have on this QRNG work here at Oak Ridge. It turned out to be really hard to implement. We've done it. We did weak measurements, or I can't even get into it because it would be too long. But it's a subfield of quantum measurements that we've done. We did this with polarization. We made the random number of the polarization of the photons, and we did a weak measurement on them, and we showed it works. But that, again, turned out to be expensive. So we went a different direction and said, instead of measuring single photons all the time, why don't we just measure a lot of photons and access the noise from the Heisenberg uncertainty principle instead? So it turns out those numbers that I showed you before, the X and the P, you don't have to measure single photons to measure those numbers. You can measure on a field of light with any number of photons in it at all. The theory doesn't change with the numbers of photons. The concept of the Heisenberg uncertainty principle is for all values of X and P. So for whatever reason, up to now, people had just been always thinking you need to use single photons to do quantum random number generators. Not the case. And there are actually papers out there, not by us, by others as well, that support this. So what we do, this is just a diagram that shows that picture, that photo I showed you before. There's the weak measurement where we ask a little bit about where's the beam pointing. Then we just change where the beam's pointing here, do a differencing on the two beams to access the what we call the standard quantum limit noise, the shot noise. Oof, I'm really behind. Okay, get nice looking random histogram out. I'm going to skip this one. This is just more stuff that we've got invention disclosure. This is the non-token version. I was telling you guys you can do this on your cell phone. I'm going to skip that. So we've been working on making it smaller, eliminating all the expensive optics, and I have some pictures of it here. We got FPGA backend for reading the data out of this guy, and let me show you some data. So here's what the quantum noise looks like. Everybody knows what white noise looks like, right? If you don't, I'll tell you it's flat on a spectrum analyzer. If you get an audio spectrum analyzer and you play white noise over a speaker, look at it on the spectrum analyzer, you would just see a flat line with wiggly grass. That's what you want to see if you want to be measuring noise. The question just is this noise quantum or not? And we characterize it. We have a way to characterize this and know that it comes from the quantum noise due to the Heisenberg uncertainty principle. So that's actually what this data shows. Here's a picture of the device that provides that noise. And here's another version of it. Actually, what we're doing is we're using light-emitting diodes, which are like less than $1. So in the past, what people would do is they'd use lasers to generate the noise, and those are obviously a laser is a lot more expensive than a light-emitting diode. We have our light-emitting diode sitting here, costs less than $1, and we have this detector here that's a few dollars. These are just op amps. Well, you guys probably know how much an op amp costs. So this is really cheap. So it turns out the expensive part of our QRNG is not the noise; it's the back end that converts this is already random. We've already generated random numbers, right? We just need to digitize them. And so we've got to digitize them. This is just the characterization that shows that they're random. Straight line means white noise. Curved line means classical noise. So we can show that our data is indeed quantum. So we need the ADC. So we hook up an ADC on a zinc berry. Right now we have a 1.3 gigabits a second transfer rate. We take the noise in, put it through a 16-bit ADC, and then what's interesting about this zinc berry device is we just dump those straight into memory. So we just dump those straight into SDRAM. Then our Linux backend can talk directly to that same SDRAM. And good, because I'm in the last couple of slides. All right, Toeplitz extractor. I don't think I need to go through this. This is just a way to get from random numbers to more random numbers. All this is that to say that we can use this extractor at a gigabit a second. Here's some examples of histograms. You start out with not very random looking stuff, pass it through our ADC, and you get this green. It looks like the blue one I showed you before. It looks like white noise, right? So we went from the flat line of the spectrum analyzer that was analog. This is just reproducing that on the digital, in the digital domain. That's all we're doing here. So the numbers are already random. We're just trying to get them into the digital domain here. And I think that's it. I don't know what happened with the formatting here. Sorry. But the point is, low-cost LEDs can be shot noise limited with cheap power supplies, and that's what they'll demo in the lab. The fact there's a linchpin piece here to some of this technology, which is that the fact that we realized you can use just a light emitting diode that costs less than $1 to access the Heisenberg uncertainty principle. For whatever reason, people have always thought you need to use lasers for that. It's not true at all. Of course, low-cost transimpedance amplifiers easily amplify that quantum vacuum noise, and we can actually measure the noise to look and see if there's bias in there, and like I was saying before, do the feedback or feed forward to correct for that. And yep, multiple ways of doing that. And I think that's it. Yes. 11:30.
So one or two questions? I have one for you.
Oh, yeah.
So you have a box in your lab that is at the prototype level.
Yeah.
And has the ability to crank out random numbers.
Yeah.
Can you talk about what it would cost perhaps in production and how close it is to being ready?
Oh, yeah, we didn't talk about the cost at all. That's right. So we've been shooting for, the first half of the talk talked about these quantum technologies, and they had these expensive detectors. And then the last half I was showing you this pretty little circuit board, that looked about this big. The idea is that all the components in there are only a few dollars for that. And then now you've got your ADC and your backend FPGA, right? Well, what do those cost? Those are typically, depending on what you choose and what you need for this project, for the level of randomness you need, those can be about $100 for those. So our ADC that we're using right now costs us $100. Zinc berries are practically like handed out for free at conferences. So you can use whatever you want for your back end. Yeah, that's what we're shooting for, is $100. Obviously in our lab it costs a lot more than that because we're putting our man time into it to develop it. But the bill of materials, I think was the question, yeah, it's probably not going to be below 100 yet, but I think with economies of scale, if we sell 1 million QRNGs or 10 million QRNGs, yeah, it'll definitely be below $100 at that point. And how close is it to being ready? That was the other part. Well, it's not all in a nice, neat little box yet. What you guys will see in the lab, if you decide to go to the lab tour, it's like two pieces plugged together, and so it's very close to all being in a nice, neat little box. So yeah, the development cost to get it there, it wouldn't be too much. It'd probably be similar to what we've already, been doing as part of the TIP program to finalize the whole thing to where we get to the next order of magnitude in terms of gigabits per second. We're at gigabits per second now. If we want to get to 10 gigabits per second, it'll probably cost us a little bit more in development cost, mainly man time again. The bill of materials is kind of already set. Hopefully that was.
Second question. So if I, as a manufacturer, could produce and sell for $200 a small quantum random generator, how many people want to buy $200?
So we did some market study. We've been working on this for a while, actually. So a while back we did a market study, and the market's only gotten bigger since then. There was ours was mainly for multi-factor authentication back then. So if you want, let's say the multi-factor, there was a prediction that the multi-factor authentication market's going to be huge. In 5 years from now, like a $5 billion market, which I'm not quite sure. I'm not an economist, but let's say it's $5 billion. Not everybody who works in that market is going to need QRNGs. So we predicted as part of that study that maybe let's say 10% of that market would be QRNGs. That's a pretty sizable market still. If the market goes to 10 billion, you're at $1 billion there. The other markets that we studied were HPC. It's a much smaller market, but you're looking at well over $100 million a year. I mean, for supercomputers alone at Oak Ridge, we spend more than $100 million. So you're looking at probably north of $1 billion for HPC. And again, what do HPCs need them for? Because people use them to do simulations, climate science, Monte Carlo for various things. If you I've already talked to people who have problems with periodicity in their Monte Carlo simulations. Actually, two random numbers would get around that for you. So again, we were conservative and we said 5% of that market. So again, you're coming up on several $100 million. You're getting close to $1 billion if that market keeps growing. So those were the two major ones. The other one, of course, everybody talks about is gambling, which is actually turns out to be a bigger market than I thought. And that's where everyone's selling QRNGs right now. I can't remember how big that market was, but it's a big market. I think the market for the real question to ask is like, what's the market for randomness and the market for security? So it should be really large. So. Okay, thanks.